welcome back. I'd like us to continue. We are in lesson 2 of matrices, and we had introduced the concept of matrices, and in our last class we were able to take a few exercises about the core concepts of matrices. Particularly, we looked into the meaning of equal matrices. We defined identity matrix, diagonal matrix. We also defined scalar matrix. And just to remind us, the identity matrix, scalar matrix, and diagonal matrix are all square matrices. They are square matrices because they are of the same order. They must have the same number of rows and the same number of columns. On the diagonal matrix, we were saying this is a matrix which will have zeros everywhere apart from the principal diagonal. So maybe a quick reminder on that, just as we set it off to today's objective. This is the case of diagonal matrix, A being the matrix defined as, let's assume it is given by 4, 0, 0, 0, 3, 0, 0, 0, 1. So this is an example of a diagonal matrix because the main diagonal, which is also called the principal diagonal, has got certain elements which are not necessarily the same, but everywhere else we have got zeros. The case of diagonal matrix. Diagonal matrix. Matrix B, being the scalar matrix, may now have the following: 4, 0, 0, 0, 4, 0, 0, 0, 4. Just as an example, this becomes the scalar matrix. So a scalar matrix is a square matrix in which the principal or main diagonal has got the same elements. The elements in the main diagonal must be similar all through. Then finally define the identity matrix, identity, which I said we are going to use identity matrix in the application part of this topic. And so we were saying an identity matrix again is a square matrix with +1 in the main diagonal. So in that case, a 3, 3 identity matrix, for example, our matrix C, identity matrix would be 1, 0, 0, 0, 1, 0, 0, 0, 1. So the main diagonal must have +1. The main diagonal must have +1 as the elements. So that is briefly what we did last time. And we went ahead to look at a question on the past paper which tested on matrix application, rather multiplication, and at the same time the idea of equal matrices. And we solved it, I remember. So we may not go back into that. Make sure you understand it well. We go straight to determinant and inverse of a matrix. This is where we begin mainly the real workings. And I want us, for consistency, we are going to begin with the total matrix. We shall begin with the total matrix. So I want us to start with what is called the determinant of a total matrix. So let's look at the determinant of 2 by 2, that is a matrix of order 2. And we now want to state as follows. We can always assume and pick any matrix. So let's assume that our matrix A is the matrix defined by the elements A, B, C, D. So if A is the matrix given by the elements A, B, C, D, its determinant, the determinant of A, would be denoted as A absolute, like that. So that's a symbol for determinant. And not only that, it is also allowed that we can say delta A somehow can also be used to denote a determinant. So these are all acceptable. Delta A or an absolute value of A. But again, for practice, we always use this symbol, the 2 bars with A inside, to denote the determinant of A. So look at it. The determinant of A is simply given by the product of the principal elements, that is A, B, A, D. You can see that. So our A would be given by A times D minus C times B. So in finding the determinant, it would be given by the product of the main diagonal minus the product of the minor diagonal. So the main being the principal diagonal, AD minus CB. That is how we obtain the determinant of a total matrix. Now, still on that understanding, it means therefore, if now we have a matrix with numerical values, now suppose we have matrix B is given by the elements 2, 3, I'm just assuming 2, 3, 1, -4, and we are supposed to obtain the determinant. Then from what we've said, B determinant should be given by 2 times -4 minus 3 times 1. And here we will now have -8 minus 3, giving us a determinant of -11. So for the 2 by 2 matrix, that is the understanding. In order to obtain a determinant, we would simply obtain it as we've indicated. Quite clear? Now let's proceed with the understanding of the determinant. I'd like us now to explain the inverse of a 2 by 2 matrix. So that is the determinant. We go to B inverse of 2 by 2. The inverse of a 2 by 2 matrix. Now, because we have taken our matrices here and we have our examples, I want to go straight using these particular examples. So the inverse of matrix A So we begin as follows, that inverse of matrix A denoted as, so the inverse would be denoted as A raised to power -1, like that. The inverse of matrix A will be denoted as A inverse, should be given by, remember our matrix A is the one above here. So assume matrix A is A, B, C, D, the elements. So the inverse of matrix A, denoted as A inverse, is given by the formula 1 all over the determinant of A into the inverse of A would be given by 1 all over determinant of A into, now look at what we are doing. We are interchanging the elements in the principal diagonal. That is, D takes the position of A, D will take the position of A, and A goes to the position of B, or rather B. Then you introduce negative here and negative here. That's how we obtain the inverse. I want to repeat. And please, as we do it, look at the original matrix A. A is A, B, C, D. So its inverse, what we say, is obtained as follows. It must be 1 all over the determinant into, now what you do, the elements in the main diagonal interchange them, such that D is coming in place of A and A goes in place of D, as you can see. Then introduce negatives on the minor. So here C negative, B negative, just like I've indicated. Minus C minus B. That gives the inverse of matrix A. It gives the inverse of matrix A. Now we can use matrix B because it has got numerical values. Let's use matrix B in our example to find its inverse. And without repeating, we have worked out the determinant of B to be -11. You remember that. So B inverse, so we'll say the inverse of B inverse would be obtained as follows. 1 all over -11. Don't forget how we obtained -11. It was 2 times -4, -8, minus 3 times 1. So -8 minus 3 gave us -11. So our determinant is -11. Therefore, we have 1 all over -11 into -4. Look at that, -4, -3, -1, and 2. That's the inverse. You are allowed to simplify further. If you wanted to simplify, it would mean we'll be multiplying the determinant with each and every element, such that in the first case, you will have +4 all over 11. The negatives will cancel out. So you will have 4 all over 11, 1 all over 11, 3 all over 11, and this would be -2 all over 11 because it is positive. So this one should take positive values, but this would be negative. But even by just indicating that B inverse is 1 all over -11 into that, it speaks that you have obtained the right inverse or the correct inverse. 2 by 2 matrix. Now, how then do we apply the knowledge of inverse of a 2 by 2 matrix? So this knowledge of 2 by 2 matrix is applicable in solving simultaneous linear equations. So I want us to look into that very quick. Now we are saying just write it. Application of inverse in solving simultaneous linear equations. We are going to do that together. We are going to apply the inverse of a matrix, of course, 2 by 2, in solving simultaneous linear equations. And I want to give us an example which we do together. So it states as follows: 2x, let me give you the equation here, 2x minus y equals 7. And this is our first equation. And the second equation reads x plus 3y equals 14. Equation 2. Now we have got two linear equations here, which I'm able to write for us. 2x minus y equals 7. And x plus 3y equals 14. Now, from what we learned previously, we were able to solve it using elimination method in our previous class. We remember the elimination method. But now, when the question is use matrix algebra, we have to use matrices in solving this. So I want to take us through the simple steps of solving this by matrices, and then it will be very clear for our understanding. Now, the first thing to do is to form the matrix out of this. And the resulting matrix will be from the given coefficients. You take the coefficients of the unknowns, that is to mean 2x, the coefficient is 2, minus y, the coefficient is -1, x, the coefficient is +1, and 3y, the coefficient is +3. So this is the resulting matrix. The resulting matrix is 2, -1, 1, 3, as you can see. Then we multiply with the unknowns in the order they were given, x being the first one and y like that. So we form what we call the column vector xy and equate it to the 7, 14 column vector, 7, 14 like that. So I hope up to that point, we have formed the matrices. The next step is to obtain the determinant. So the determinant of the matrix, let's assume it is matrix A. So the determinant A, from what you've said, the determinant of matrix A will be given by 2 times 3, which is 6. So it is 2 times 3 minus -1 times 1. And accordingly, this will give us 6 plus 1, because minus minus is positive. The determinant is 7. So our determinant obtained is 7. So we have said the first step, form the matrix, which we have formed 2, 1, -1, 3. You must indicate the unknowns with their column vector or column matrix, x, y in the order they were written. X was the first one, followed by y. Then we equate it to the column vector 7, 14, again in the same order. So we have obtained the determinant. The next step is find A inverse, the inverse of A. And accordingly, A inverse should now be 1 all over the determinant, that is 1 all over 7. The inverse of A is 1 all over 7 into the interchange of the elements. Look at it. Principal elements. 3 taking the position of 2, 2 taking the place of 3, like that. Minus 1, introduce minus 1 here. And then, since this is negative 1, and we are introducing negative, this is now positive. Take note of that. The original matrix is here, 2, negative 1, 1, 3, and we say in finding the inverse, now we must interchange the principal elements like we have done there, 3 taking the place of 2, 2 taking the place of 3. We have interchanged it accordingly. Then the next thing, introduce negative. You must introduce negative on the minor diagonal. So, because it is positive 1, it comes to negative 1. Because here it was originally negative 1, when you introduce another negative, negative makes it positive. That's the emphasis I wanted to make on that. So, already we have the inverse of matrix A. The inverse of matrix A is already obtained. Now, with the inverse of A obtained, already we have got the inverse of A. Remember, we are using the application of inverse in solving the simultaneous linear equations. Now, how do we apply that? I want to give you the understanding, then we can be good at it. Let me just go away with this upper part so that we follow what I'm exactly doing. Up to the point we have obtained the inverse, I would want us to take note. We need to note that, and this is something we must all take note of, that we need to recall or note, if we have the inverse of matrix A, that is the original matrix A times its inverse, that is A times A inverse, it should give us an identity matrix, I for identity. That one we must write, that A times A inverse, if you have the matrix A and you multiply by its inverse, it would give you an identity. And that is a rule, you don't even have to prove it. Just by stating that A times A inverse gives an identity, it gives us a lot of meaning. Now, why did we do that? So that what we needed to write after obtaining our inverse, remember our inverse is here, 1 over 7 into that. Don't forget our inverse. Then we needed to come here and state as follows. Let me just continue with the problem, solving the problem. Now, we needed to come here and state as follows. The original matrix A is 2, 1, minus 1, 3, multiplied by the inverse. The inverse is 1 over 7 into 3, negative 1, 1, 2, multiplied by the column vector x, y, like that, equate it to the inverse, equate it to the inverse still 1 over 7 into 3, negative 1, 1, 2, multiply with the column vector 7, 14. Please let's take note of that step because it is the most important step in applying the inverse of a matrix in solving simultaneous linear equations. Just take it down because you will use it for reference. That if we have the original matrix A and we multiply it with its inverse, the resulting matrix is an identity matrix. Why did we have to write all this? Such that now what we have on the left-hand side of the equal sign, on the left-hand side, you can see my left-hand side, you should now be left with only x all over y. And I said you don't have to prove that A times the inverse is identity. By simply stating this, it is understandable that on the left-hand side, we'll be left with xy is equated to the right-hand side is still 1 all over 7 into 3, 1 minus 1, 2, like that, multiplied by 7, 14. We are simplifying further, so it is a step by step. So let's get up to this point together. xy column vector is equated to the inverse times 7 all over 14. Or rather, not 7 all over 14, but by the column vector 7, 14. Now, the question is, how do we proceed to obtain the value of x and the value of y? Very simple. Let's view what I'm doing. In order to obtain x and y, I want to begin with x and just follow my steps. To find x, it will be given by, remember x is the upper element here. So I'm using the upper row in obtaining x. So to obtain x, use the upper row. To obtain y, use the lower row. And this is how it is done. We are obtaining x. Using the upper row, 3 times 7. X is 3 times 7. That is 3 times 7. 3 multiplied by 7 plus 1 times 14. Plus 1 times 14. We want to obtain x, 3 times 7 plus 1 times 14. All is divided by 7. Because, remember, 1 all over 7 is outside the bracket. So what I'm just simplifying. And this would give me 3 times 7 is 21 plus 14 is 35. Divide by 7, the value of x is 5. The value of x obtained is 5 when you work out that. Let's obtain y. To obtain y, use the lower element because y is the lower one. So how do we go about that? Negative 1 times 7 minus 1 times 7 plus 2 times 14. Minus 1 times 7 plus 2 times 14. 2 multiplied by 14. All divided by 7. Don't forget, it was 1 all over the determinant times that. That's why we are dividing by 7. So this gives me negative 1 times 7 is 7 plus, that is negative 7. Negative 7 plus 28 is 21. 21 all over 7 should give me 3. So accordingly, we have been able to solve the linear simultaneous equation through the inverse method, that is the application of inverse to obtain that, and x is 5 while y is 3. Is there any question up to that point? The value of x is 5. I hope we have followed the steps. and the value of y is 3. I want to welcome any question before I give the alternative method. There is an alternative method which is very interesting. I want to explain the alternative method. Any question on that? Fine. So let's take the alternative method. So the alternative method, call it Cramer's rule. I'm going to illustrate it. We are using the same problem. We are not changing, but using the same problem. So up to that point, we should be together. Let's call the alternative method as Cramer's rule. Never mind about the name. The most important thing is to understand. So we are looking at alternative method. Apart from inverse method, that first method is the inverse method. That's why accordingly I call it application of inverse. So the alternative method, call it Cramer's. That's the name of a person, Cramer's rule. The Cramer's rule. Alternative method is accordingly referred to as the Cramer's rule, and we are using the same example. So without repeating, we obtain our matrix. First of all, we must form the matrix. So you remember the question as it was given, the simultaneous, obtain the matrices. So I'm just going ahead from the matrices, how we obtain them. So the obtained matrices were 2, -1. I hope that is the original matrix. 1 and 3. You must indicate this. X, Y was equated to 7, 14. That would be the first step. Because if you opt to use this rule, you still have to form the matrix. The matrix would always be seen. Remember, now, the name is very interesting because somebody may ask me, does it mean now we cram? Please, we are not cramming. I know the crammers would be accordingly interpreted as cramming. You know the literal meaning of cramming. Cramming ni ile unaweka tu kwa akili by force. What should happen? No. But that is just the name of the person. Very interesting name. But let's go through it together. Now, in the Cramer's rule, it's very interesting. And probably it could entail cramming, but let's do it together. So once we have formed the matrix, look at what I do. In order to obtain X, it should be given by, remember, X is the first unknown in the first row. So if you want to obtain X, we are replacing the first column of the original matrix with what we call, anyway, as we are going to proceed, I'm going to take us through the input-output model. We will be referring to this one as the demand matrix. But never mind, what is important is to follow. So if we want to obtain X, X would be given as follows. Replace the first column with the demand vector. That is, look at what I'm doing. X would be given by 7, 14. So this column vector, replace it with the first column. Retain the other column, -1, 3, bracket, Divide by, this one is divided by the determinant. Divide by the determinant. Let me just indicate the determinant. Let's assume it was matrix A. Divide by the determinant of the matrix A. I repeat, I want to repeat. Cramer's rule. First of all, form the matrix. That is step 1. In fact, I skipped step 2. Step 2, determinant A, of course, we know how we obtain that, is 6 plus 1 give us 7. B, 2 times 3 is 6 minus 1 times -1. So minus 1 plus 1. So this is step number 2 in the Cramer's rule. We have formed the matrix 1. We have obtained the determinant. Step number 3, here we are. Now with the determinant obtained, now let me replace this with the correct actual value of determinant, which is 7. Now look at it, the Cramer's rule. Step 3 is very important. What are we doing? To find x, x being the first unknown in the first row, you need to replace the first column with the column vector 7, 14. Retain this as it is. So now what we have, look at it. What we have, very interesting, is that this one will give us 7 times 3, just the normal way we are working the matrices. 7 times 3 minus the bracket of 14 times -1. This is divided by 7, and accordingly it gives 21 plus 14, 21 plus 14 all over 7, giving me 35 divided by 7, and the else is 5. Just like we obtained it using the inverse method. To obtain y, just to continue, y should be given as follows. Cramer's rule. Return column 1 in the original matrix. Return column 1, 2, 1. Replace column 2 with the column vector matrix 7, 14. Divide by the determinant 7. And this one gives now 2 times 14. 2 times 14 bracket minus 1 times 7 bracket divide by the determinant 7. It gives 28 minus 7 all over 7, giving me 21 all over 7, and the value of y is 3. Cramer's rule. Now, I'd like to ask you, which one would you prefer? Assuming you are not restricted, which method will you prefer? Faith?
The second one. The second one. The Cramer's rule.
You find the Cramer's rule easier?
Yes.
Okay. So let's just agree, when you are not limited, that is, if the question doesn't specify and it is just solve the simultaneous linear equation using matrices, then I want to say you are free to either use Cramer's rule or the inverse method. But the question would be very particular, using matrices. So in using matrices, either Cramer's rule or the inverse method is acceptable. But when the question is about using matrices, please don't eliminate. I know we started from the elimination method. Don't eliminate. If you use the elimination method, you will not be answering the problem, where the question is use matrices. So in matrices, we can either use the inverse method or the Cramer's rule method. But why do we emphasize on the inverse method? It is because most of the applications, and we are going to look into the question papers, most of the applications here would specifically require the use of the inverse method, especially when we'll be looking into a 3-3, and by the way, that is my next understanding. So far, we have used the 2-2. Remember, we have explained the determinant and inverse of a 2-2 matrix and the application of the same. So can we move on? Now, the most important bit is what we are just beginning now. The 3-3 matrices. It's a bit a technical area, and I want us to take our time to understand together. A bit technical because, again, it is what is commonly tested, the 3-3 matrix. So let me take us through that, then we'll be actually good at it. Right, and maybe after the 3x3, we'll be almost home with the topic matrices. I want us to do the 3-3, and then thereafter we'll go through the application of this 3-3, which is very, very important. Because most questions in this area of majorly will require the understanding of a 3-3 matrix. So as part of our objective, have the subtitle determinant and inverse of a 3-3 matrix. Determinant and inverse of a 3x3. Determinant and inverse of a 3x3 matrix. That is an entire objective, very important, which I'd like us to take our very good time to understand together. Determinant and inverse of a 3x3 matrix. Okay. Now, let me pick a 3x3 matrix. Allow me to pick one 3x3 matrix, which we are going to use. I will give just an example of this 3x3 matrix. So allow me to pick the matrix 3, 2, -1. So this would be our example. Three, 2, -1. That is the first row. 1, 1, 1, 1, 2. Second row. Third row, 1, 0, 1, 0, -1. Let's call our matrix. It is the matrix B. Let us name it B. Correct. Our matrix B is given as follows: 3, 2, -1, 1, 1, 2, 1, 0, -1. Our objective, first of all, is to find the determinant. Now, I want us to go through the understanding. There are two methods of finding the determinant of a 3x3 matrix. And the two methods are, the first method, let me call it cofactor method. You could also call it cofactor method. The cofactor method, and we'll go through it together. Now, The starting point would be to understand, and this, let's take every note as we go through this, that the signs, there are certain signs which we must use in the cofactor method, and these signs are as follows: plus, minus, plus, minus, plus, minus, plus, minus, plus. And I would like us to take it as such. We will be using that, therefore we must write it. I repeat. Of course, the first method is the cofactor, but these signs will be useful: plus, positive, negative, plus. We will be explaining why we are doing this. Negative, plus, negative, plus. But we must write, then we will be able to follow. Remember, it is the cofactor method. Now let's get to understand it jointly. And if you want to go through this method, you must be very consistent. And that means we want to go per row. I will clarify and give the meaning. So let's take the first row. We want to find the determinant using the first row cofactor method. This is what we are supposed to do. And I've said we are using the first one. So the first element is 3 in row 1. So with element 3, we are going to ignore. You ignore its column and the row, and then you pick the remaining elements. Look at what we are doing. So that should give me 3 into 1, 2, 0, -1, bracket. I want to repeat what I've done. I just want to repeat what I have done here. We are saying if we take the first element in row 1, row ni equal to 3, 2, -1. Well, of course, all of us, we know what a row is. So we want to find the determinant using row 1. And by the way, you can use any row to find the determinant, provided you are going to follow the rules. Plus, minus, plus, and I will tell us where does that come in. But first things first, I'm saying if I pick element 3, I ignore its column and the row, I will be left with 1, 2, 0, -1. And that's what I have here. So I have 3 into. So 3 being that element into 1, 2, 0, -1 bracket. The next element is element 2 in row 1. It is element 2, but remember, I've said here plus, and I'm still in row 1. So row 1 should have positive, then negative, then positive. Therefore, if the second element is element 2, I come here and indicate -2 into, now what do we do? Look at it, just follow. Element 2, we are doing the same thing. We ignore that entire row and the column where 2 is. If you ignore the entire row and the column, you'll be left with 1, 2, 1, -1. I hope you followed how I'm getting 1, 2, 1, -1, brackets. Let me just repeat that for clarity. Remember, I've said in this case, we only want to use row 1 to obtain the determinant. So, cofactor method. Plus, minus, plus. Up to that point, we are together. It explains why I have -2 now. It is because of minus here. The -2 into. Now, what did I do here? For the element 2, you ignore the column. Each element, you must ignore the column and the row such that you pick what is left. So 2, if you ignore its row and the column, what is left will be 1, 2, 1, -1. That's how I obtain the bracket. Then finally, and let's follow please, we are at -1. In row 1, the last element, row 1, column 3 is -1. Originally it is -1. In my signs, the sign states plus. Mathematically, positive cannot change negative. Therefore, it remains to be -1 into, we ignore the row and the column, we are left with 1, 1, 1, 0 into 1, 1, 1, 0, close the bracket. What do we do with this? What do we do with this? Whatever we have obtained, let's follow to join together. This should give me 3, which is outside the bracket, into, please, up to this point, I just want to believe we know what we are doing. Always, we multiply the main diagonal, we minus the other one. So, I just want to sum it up by working. 1 times -1 is -1 minus 0 times 2 is 0. So -1 minus 0 would still remain to be -1. That is the bracket of the first bracket. Minus 2 into 1 times -1 is -1 minus 1 times 2 is -1 minus 2 is -3. That bracket should give you -3 because 1 times -1 is -1. When we minus 2, we get -3. That is because 1 times 2 is 2. In other words, -1 minus 2 is -3. That is how I'm getting this one. Then -1 into 1 times 0 is 0. 0 minus 1 times 1 is -1. So here it is -1. Sometimes students miss these things because of the wrong use of signs.
Mi check shemejio yenye unajua niliomba mapema ile siku. So
let me just repeat what we've done here. What we are doing is multiplying the main diagonal. 1 times 0 is 0. 0 minus 1 times 1 is -1. So that is how I obtain this. What is our result? Look at our result. Our result would be -3 plus 6, because -2 times -3 is +6. -1 times -1 is +1. So the answer, the determinant is -3 plus 7. The determinant is +4. The answer is 4. Cofactor method of finding determinant of 3 by 3 matrix gives us a matrix of, a determinant of +4. The matrix so obtained is, the determinant is +4. Cofactor method. Now, I'd like to give a very small exercise. Can we try? You know, the rule is, please let me be very clear on this. We have used row 1. Is it possible from where you are, you use row 2 and see whether you can find the same determinant? Can you try that from your end? I want to repeat my question. My question is, can we possibly use row 2 of that matrix B to obtain the determinant following the steps I've used in row 1, only that now in row 2, the signs are negative plus negative, meaning in row 2 you will begin as follows: -1 into whatever you will find, and you continue following the signs for row 2. The signs for row 2 reads negative plus negative. I want to hear from us, and let me get a confirmation from Kimathi. Kimathi, can we try using row 2?
Yes.
Yes, please, let's try. And in case you get stuck, anyone you get stuck, you let me know. We can try that in a moment.
Okay.
We are using row 2 to prove if our determinant will still be +4, because whichever row you pick, the determinant is not going to change. The determinant will always remain to be the same, provided we are doing the right thing. So I want you to try from your end using row 2.
Negative. Negative. The quantitative one. Plus -1.
Anyone who is already there? I know we are trying to figure it out. We are using row 2 to obtain that determinant. cofactor method. This is now the so-called the cofactor method. Cofactor method, we have no choice. It's a very important understanding because we are going to use it still further than this. Further than this, we are still going to apply the idea of the cofactor. So we must just know it. We must just know it in totality. Yes, any one of us who is done? We are using row 2 to determine the determinant, and our goal is to confirm if by using row 2, we are still able to get determinant to be positive 4. We are taking time on that deliberately so that we understand. I have a reason why we have to do that and internalize it, because it would be very useful. So please, everybody should try such that even if you make a mistake, we can correct together because it's very necessary. And again, we are going to use the same matrix to explain how to go about inverse of a 3 by 3 matrix. The inverse of that's why the cofactor method is important. Anyway, you will understand why I'm saying that. Inverse of a 3 by 3 matrix. Okay. Let me do as you correct yourself. I know it's better that way. The same understanding, you will be correcting yourself, and it would only help you if you tried. It really helps. Even if you tried and you did not get it right, you will really understand now. But it can be unfortunate if you never tried. So let's do it together. We are going to do it together. Remember, we have said we are using row 2, using the same method to obtain our determinant. We are going to use row 2. Now, the signs still reads minus, plus, minus. So what did we have to do with that? Row 2. Row 2, the first element is 1. So the sign is minus. So accordingly, I need to have -1 into, if someone who is keen should now understand the idea of cofactors, that the element you pick, you must ignore the column and the row, then you are left with the remaining. So for this one, if I ignore the row and its column, I will be left with 2, -1, 0, -1, like that. The second sign is plus now 1 into, now I'm here, still row 2. But now I have to add plus 1. Yes, accordingly it is plus 1 into. So for this one, I ignore its column and the row. Column, row. I'm left with 3, -1, 3, -1, 1, -1, like that. Close the bracket. Then finally, the sign is minus. So it is -2 into, -2 into, remember we were using row 2, so you stick to that row. -2 into, I ignore its column and its row, and you need to see if you ignore the column and its row, you are left with 3, 2, 1, 0.
1, 0.
3, 2, 1, 0 into brackets. If we simplify this, we should have -1 into, so the bracket is 2 times -1. 2 times -1 is -2 minus 0. So -2 minus 0 remains to be -2 anyway. 2 times -1 is -2 minus 0 is still -2. Plus 1 into 3 times -1 is -3. -3 minus -1 reads. So when I have -3 minus -1, it comes to -3 plus 1, and that is -2. So the bracket here is -2. Yes, somebody is wondering. I can still repeat what I've done. In the second case, 3 times -1 is -3 minus 1 times -1. So 1 times -1 is -1. So it reads -3 minus -1 is 3 plus -3 plus 1 minus positive. So it's like you have 1 minus 3 giving you -2. You must always view that. Then -2 into 3 times 0 is 0. 0 minus 1 times 2, that is 0 minus, that is -2 like that. Look at our result. Our result should be 0 minus, 0 minus 2 is -2. So -1 times -2 is +2. +2 minus 2 being 1 times -2 is -2. -2 times -2 is +4. Hence the determinant is +4. We have no choice, like I was saying, but to know how to obtain the so-called cofactors. And we have clearly seen them. Now, this has confirmed for us that whatever row you pick and you are using the cofactor method of getting a determinant of 3-3 matrix, it will always give the same determinant. And therefore that means even if we used row 3, the determinant would still be +4. But I don't want you to prove that. We have compared row 1 and row 2. And even if you were to use row 3, your determinant would still be +4. Don't forget, if you decide to use row 3, the signs are plus, minus, plus. Your bracket here, plus, minus, plus, minus, plus, minus, tusisahau. And it is written the way I've written it, and it is followed that way. Now, this is cofactor method of obtaining the determinants. Now, allow me to go through, before I give you the alternative method of finding determinant, I'll give it. I really want to use this data. This whole information we have used here for both Pro 1 and Pro 2, I want to use it in explaining how we obtain the inverse of a 3 by 3 matrix. After I've explained that, I will still come back to give you the alternative method of finding determinant of a 3 by 3 matrix. This method is the cofactor, but there is still method 2. But method 2, we will summarize with. So before we get to method 2, I want you to write inverse of a 3 by 3 matrix. So far, what we have done is to find the determinant. So we are going to find the inverse. So I want to retain these ones purposely because I will use them. These workings here, they will help me somewhere, but let us go through the steps of finding the inverse of a 3 by 3 matrix. And we are using the same matrix, so we use the same matrix such that we are able to follow what we are doing. And on this one, I told you, we are taking our good time. That's why I'm doing it in that stepwise approach. If we go the stepwise, it is easier to follow than if we appear to be in a hurry. So that's why I'm taking us step by step. The now objective is inverse of 3 by 3. And to make our understanding simpler, we are using the same inverse B of matrix B, which you have. Inverse of a 3 by 3 matrix. And step by step, Roman 1, find determinant. Find the determinant. In our case, we are not even repeating because we have done the workings. That's why I told you I'm returning this one deliberately. But let's go step by step. Find the determinants. And accordingly, our determinant for the matrix B, i.e., determinant B equals 4. The beautiful thing is that we have worked it out. So now everybody knows how we arrived at 4 in the determinant. Step 1, find the determinant, i.e., our determinant for matrix B is 4. We are using matrix B. Step number 2. Now this is what I want you to follow, and it is the reason why I told you I was keeping this data purposely. I was keeping this data purposely to explain this step 2. And by the way, just by the way, as we go through this step 2, I would want to say it is the main area of applying matrices. And you will understand why I'm saying so. So in step 2, we are saying obtain the cofactor. Obtain the cofactor matrix. Step number 2, obtain the cofactor matrix. And please let me guide us. Faith, kindly mute your mic, or I can mute it from my end. Thank you. Yes. So obtain the cofactor matrix. Judith, mute your mic. Judith, mute your mic. Thank you. Obtain the cofactor matrix. Now, let's have a look at it together. And I did this, like I said, purposely, such that we are good to understand and we don't go into so many workings. We still have to recall that the signs remain plus, minus, plus, minus, plus, minus, plus, minus, plus. And now I have one concern, even as we proceed. This is my concern. Whatever we are learning, I don't know what happens to somebody who misses this class. I don't know. And this is not to threaten, but you people, you understand what I'm saying because you are following the steps. These steps, even if you are to have the notes, I'm not sure how best those notes will help you. I think somebody is now confirming why I said, in most cases, some of these concepts we just have to be in attendance. That is on a very light note, but you can agree with me or fail to disagree, but that is what it is. Now we are obtaining the cofactor matrix and we stick to our signs, plus, minus, plus, minus, plus, minus, plus, minus, plus. What do we have to do with that? Without going into much workings, the cofactor matrix. Remember, in our workings, we had used row 1. There is a slight difference here, what I'm going to explain. And in row 1, we were able to obtain the element in the bracket here. You know how we obtained it, is -1. So when it comes to the cofactor matrix, for the first row, look at how we are obtaining it. It reads plus, minus, plus. So the first row, I will pick this one here, the way we obtained it. You know how we arrived at -1. And because the sign is plus, a positive sign cannot change a negative sign. So the first element of the cofactor would remain to be -1, being this element here. Now, the second bracket in our row 1, we were obtaining -3, but the sign here states minus. So it's like we have -3. The second element here is +3 now. The final element in our row 1 was -1, but the sign here is plus, so it remains -1, like that. I will always repeat, so don't worry, for clarity. We want to obtain the cofactor matrix. And let me just clarify what I'm doing. You remember, I'm looking for space. The original matrix, let me just go back to the original matrix. I said we'd rather take our time, but we understand. So the original matrix, as we had it, this is the original matrix. It was 3. Is it even visible? Yeah. Let me use some more bold pen. The original matrix here was 3, 2, -1, 1, 1, 2, 1, 0, -1. This is our original matrix, which is accordingly matrix P. And we were able to obtain its determinant. So, without going into many words, that's why I've rewritten the original matrix. I'm just guiding us, and I know once we understand, we will be good to solve the problems later on. But for now, it is the understanding. So what am I doing? Look at it. I'm not changing. Actually, what is changing is having these 3 outside, -2 outside, and -1 outside, and finding the determinants. But what did I do? Let me just help us understand. This is what I did. To obtain the first row of the cofactor matrix, this is what I did. You can have our element 3. So element 3, when we ignore the row, when we ignore the column and the row, we were left with 1, 2, 0, -1. What we have into the bracket. Now, what we have into the bracket, if we solve it, we were saying 1 times -1 is -1. Minus 0 times 2 is 0. So that is where we got -1. So because it is -1 here, so in finding cofactor matrix, you don't have to use the 3 outside. That is now the difference. So we obtain -1. So that -1, I have it here. In as much as the sign says plus, I explained a positive cannot change a negative result. So when you have a negative result, it remains to be negative, even if it is supposed to be positive. But a negative will always change a positive result. Now let me go to the second element 3, how I obtained it. Cofactor element. So I'm now at 2. So at 2, if you ignore the column and the row, you are left with 1, 2, 1, -1. What you had here. And accordingly, it gave us -3, being 1 times -1, -1 minus 2, -3. However, if here it is -3, inside the bracket here it is -3, my sign reads -1. So I'm saying -3 changes it to +3. So that is what I wanted to really stress on, so that we view it together. Therefore, because we had done this, -1 and the positive sign is here, positive cannot change negative, will turn negative. Going by what I've said, row 2 should now be as follows. Look at my row 2. That's why I retained this one purposely. You know what we are doing? Just focus on the values into bracket. In row 2, the answer into bracket is -2. And because it is -2, my signs are minus. Minus, -2 would now change row 2 to be +2. So here you have 2 positive. Cofactor matrix 2. When we proceed here, inside the bracket is still -2. And the sign here is plus. This positive cannot change negative. It remains -2, like that. The last bracket is -2. But the sign is negative. Minus -2 should now make it +2. That is row 2. Now let me go to row 3. We had not done row 3, such that we follow. We are at row 3, the original matrix, and we want to obtain the cofactor matrix. Look at our original matrix in row 3. Here we are. Row 3, the first element is 1. I'm not writing again because we need to see. We have said so much. We want just to work out and place our row 3 elements in the cofactor matrix. So in row 3, the first element is +1. The rule is simple. Ignore the column, ignore the row for +1. we are left with 2, -1, 1, 2. If you go by what we are doing, it should be 2 times 2 is 4. 4 minus -1 is +5. We have 2 times 2 is 4. 4 minus 1 times -1 is 4 minus -1, +5. And because, +5. And because it is plus, it remains to be 5. So here is 5. Let me repeat. Last row, the element is 1. When you ignore the column and the row, we'll be left with 2 times 2, 4. 4 minus -1, +5. The sign is plus in the last row. The next element is 0. So 0, if you ignore the row for 0 and the column for 0, you are left with 3, -1, 1, 2. For me, I'm just seeing them. If I ignore the column where 0 is at the row, I will be left with. So let me just write that 0. Nitabaki na 3 minus 1. You should be able to see that 1, 2, something like that. So that gives me 2 times 3, 6. 6 minus -1, +7. It is +7, the result, but it states negative. A negative will change the positive. So the cofactor matrix is -7. Not positive, but -7. The cofactor element is -7 because the sign here is negative. Now finally, is -1, the original element, -1. When you ignore the row and the column, you will be left with 3, 2, 1, 1. And that result is 3 times 1 minus 2 is 1. 3 minus 2 is 1, and that is positive. Positive. And even here it is positive. So, +1. And we are done with the so-called cofactor matrix. I want to stress, in the application of this matrix algebra, there is nothing as important as knowing what we have talked about in finding the cofactor. I would want to give you time, follow the workings we have done today such that we internalize why are we obtaining these cofactors the way we have obtained them and with the very signs. For example, why are you obtaining this to be -7? The explanation is here and we have done it. Remember what I'm saying. Each original element you pick, you ignore its column and you ignore its row, then you take the approach of finding the determinant like we did say in total. You multiply the principal element, the principal diagonal, you minus the other one. So that in our case, when we obtain +7, we are now saying the cofactor matrix, if it was +7, it is changing to -7 because the sign here is supposed to be negative. So this bracket I used for the signs is very key. And we must always remember it as the gospel truth, for lack of a better word. And it is not something you will even struggle with. Hata ukisahau, you can remind yourself that it begins with the positive, and then they alternate. Positive, negative, positive. Ukitoka hapo minus, plus, minus. Then you go back to positive, negative, positive. You can never forget that. Even if it means mastering. Now, I can do away with this. You can now understand why I reject them. It is because I wanted to use these values, which we know how we were obtaining. The -1, the -3. Now this -3 changed to +3 because of this negative. This was -1. It remained -1 because a positive cannot change a negative. I also returned this one purposely that into bracket we had -2. That -2 changed to +2 because of this negative. Here it is -2, but if here is plus, it remains -2 because positive cannot change the negative. Finally, here it was -2, but the sign is supposed to be minus. -2 changed it to +2. I cannot overemphasize that. Let me do away with this. Then, and the whole thing, remember, we are working, what is the inverse of a 3 by 3 matrix? That is what we are doing. And we are just at step 2. And step 2 is the only technical step, because now I want you to write step number 3. Step number 3 is quite easy because it states find step 3. And I told us we are doing step by step. That would help us. Find the adjoint matrix. Find what is called adjoint matrix. And you know, we are even explaining the technical terms in a very simplistic approach. Find the adjoint matrix. You see, when somebody hears adjoint, you may wonder, what is now that? Very simple to find, and now we are not even going to overstress because we have done much of the working. So simply say, in find the adjoint matrix that is equivalent to cofactor. It is the cofactor transpose. Someone who remembers, a good student, would remember that the transpose of a matrix is just the interchange. Find, because I explained when we introduced the unit. Find the adjoint matrix, and the adjoint matrix is simply explained as the cofactor transpose. Look at it. Very simple. We will now say our adjoint equals. Now you don't work any further. That's why I was stressing. The moment you obtain the cofactor, your work is done. So look at what I'm doing. Adjoint equals, if it is cofactor transpose, look at my working. Very simple. Row 1 minus 1 positive 3 minus 1. It becomes column 1. So just do this working. Simple. Minus 1, 3, negative 1. Positive 2, negative 2, positive 2. Positive 5 minus 7, positive 1. And that is done. Transpose cofactor to get the adjoint matrix. I repeat, what I'm doing to obtain the so-called adjoint is just to interchange this thing. Hii iko hapa juu. Hiyo row ya kwanza inakuwa column ya kwanza. Row ya pili imekuwa column ya pili, na row ya tatu sasa imekuwa column ya tatu. Who cannot do that? Nobody. So that's why I said the whole work is here. The moment you obtain the cofactor, you are good at home. You can never miss the application of these matrices. And we conclude, therefore, after obtaining the adjoint, look at how interesting it is now. Roman 4, the inverse, because that was the objective, inverse is equal to 1 all over determinant. The inverse of the 3-3 matrix is equivalent to 1 all over determinant multiplied by the adjoint. And that is how simple our work can be made. That the inverse of the 3-3 matrix, as we conclude, the inverse of a 3-3 matrix would be defined as 1 all over the determinant times the adjoint. which in our case, therefore, because we have done everything, it should be 1 all over 4. 1 all over 4, that was the determinant, and that's why we started from that point. 1 all over 4 into the adjoint matrix, again, which we have just interchanged right now, -1, 2, 5, 3, -2, -7, -1, this is 3. Just rewrite your adjoint, 2, +1. And with that, we have obtained the inverse. You don't even have to simplify as it is. Our inverse is 1 all over 4 into the adjoint, which we obtained by transposing the cofactor. That is what is expected of us. And you can now appreciate why I said it is very important when we understand the step of obtaining the cofactor matrix. I would want you to take your very good time before our next meeting because of time, and I know it will not be meaningful to talk about the applications, which is the very last objective of matrix algebra. So we can keep that when the brain will be very fresh, such that we do it together. Now, I promised as we conclude to give the alternative method. That one you will just take it as your note, a point to note. The alternative method of finding determinant. That is what I want to state in just 5 minutes or less, then I give you the break. Otherwise, make sure you have followed these steps for finding the inverse of a 3-3 matrix up to the point we have concluded that it is 1 all over determinant times the adjoint. We will really use this knowledge in the application. Now, if that is taken, a point to note, you remember where we started to find our determinant, how we were obtaining 4 using the cofactor method. Now, I'm giving you the alternative method, and it is just a point to note. The reason why I gave the cofactor method is because in the application, we will mainly use the cofactor in the application of matrices. So it is very important that we understood that cofactor method of finding determinants. However, the alternative method is called determinant by determinant by artistic method. This method is called artistic method. Maybe it would be easier. Every time I give an alternative method, people find it to be easier. And I don't want to deny that fact. If it is easier, well and good. But what I've said, the reason we have looked into the cofactor method to find determinant, it even introduced us to the understanding of finding cofactor matrix. Because in the application, it is the cofactor matrix which will be very, very important to obtain. So all is not lost. But let me explain the artistic method. I still pick our original matrix, the very example, the matrix B. So our B matrix is originally 3, 1, 1, 2, 1, 0, as it was originally, -1, 2, -1. Remember, this is just a point to note in finding the determinant. And I want to leave it optional It is not mandatory. I will want to make it optional for you, whether you will find it easier to use or not. Now, in this method, the first thing to do, just follow it the way I'm doing it. Write the first two columns on the right-hand side of the matrix. See what I'm doing. First two columns on the right-hand side of the matrix would give me 3, 1, 1. Hii ni ya kwanza. Ya pili, 2, 1, 0. So I've added the first two columns. I've added the first two columns on the right-hand side of the matrix. Now, once we have done that, we want to obtain 3 diagonals, 3 main diagonals. And because I would want you to see, just allow me. Otherwise, if you are writing, you know my writings are a bit stunty because of the whiteboard, but we should be able to see this. We want to extract 3 diagonals, complete diagonals. The main, and then we do the minor. Look at what I'm doing. To obtain the diagonals, 3 complete diagonals, you don't have to really do this. I'm just doing so that we can see. That is the first one. This would be the second one. And this is the last one. Principal diagonals. I hope if you are writing from your end, and you can even use a ruler to cross them, you can see if you added 3 columns, this end, sorry, 2 columns, and you have to draw complete diagonals, you should be able to extract them using those elements. Let me, yeah, correctly. If you are using a ruler, it looks even clearer and better. Once you've added the first 2 columns, you need to draw the complete diagonals with the ruler like that. I was just using that one so that you can extract and see. So these ones are principal diagonals. And because I really want you to see, this is what I do. I will now take 3 times 1 times -1 plus 2 times 2 times 1. And of course, you can see where that is coming from. Plus -1 times 1 times 0. These are from those principal diagonals. This one, I put a bigger bracket, minus the next one. Now you do the reverse. Look at the reverse. Let me try to use crossings, straight lines. The reverse, complete diagonals, you can get a better one. There is 1, 1, -1 is complete. There is 0, 2, 3 complete. I know from your end you can view what I'm doing and get exactly -1 through 1 to 2. That is, it can be so congested, but whichever the case, just follow what I'm trying to do. That is now minus. There is 1 times 1 times -1. I'm very sure those who are doing are able to see what I'm doing. Plus, hii ya pili ni 0 times 2 times 3. Actually, whatever you're multiplying with 0 will always be 0. Then plus -1 times 1 times 2. And with this, we can summarize 3 times 3. Sorry, I just want to summarize 3 times 1 times -1. That is 3 times -1 is -3. 2 times 2 is 4. 4 times, that is 4. So plus 4, hii itakuwa 0. So the first big bracket even gives me 1. The second one, 1 times 1 times -1 is just -1. 0 times that would be 0. Negative 1 plus 1 times 1 is 1 times 1 is negative 1, negative 2. So what do I have? I have negative 1 plus negative 2, giving me negative 3. Such that this was positive 1. 1 minus minus 3, positive 4 is the determinant. 4 is the determinant. Please, whether artistic method is the best for you in finding determinant, I would leave it for you to judge. And with that, we have come to the end of today's session. In our next class, and the very final class for matrices, we are going to major on the application, and that will be guided by the past papers. Any